Now let's review conditional probability. In a certain city, 45% of registered voters are Republicans, 40% are Democrats, and the rest are independents. So that would mean 0.15. Also, 40% of Republicans are women, 55% of the Democrats are women, and 60% of independents are women. So let's take a look. So I know Republican, Democrat, and independent. So I know these things: 45%, 40%, and 15%. Now I can break these down into two more categories. So I have men and women. We were given the women information. So that means I know that 40% of the Republicans were women, so 60% were men. 55% of the Democrats were women, so 45% were men. And 60% of the independents were women. So if I just multiply all of these all the way across, I end up getting all of the probabilities. So probability of a Republican male is 27%. Probability of a Republican female was 18%. Probability of a Democratic male is 18%. Probability of a Democratic female was 22%. Probability of an independent male is 6%. And an independent female is 9%. Suppose you randomly selected one registered voter. What's the probability that you choose a person who is a Republican and a woman? We already calculated that to be 18%. Probability that somebody you choose is a woman, we just add together all of the woman categories. So we had 0.18 plus 0.22 plus 0.09. So those are the three woman categories that we have. That's 49%. What's the probability that you choose a person who is a male or an independent? So I just found out that 49% were women. So in the binary calculations of this problem, we have 51% are men, and then I need all of the independents that aren't men in order to easily calculate this. So that ends up being 60% of all people were male or independent. I likewise could have just calculated the number of independents, which is 0.15, and then add together all the males that aren't independent. So that would be 0.18 plus 0.27. If I add those together, I also get 0.6. So there are several different ways I could have calculated that. What's the probability that a randomly chosen male is a Republican? So the probability of Republican given male is the probability of Republican and male, which was 0.27, divided by the probability of being a male, which was 0.51. So if you're given that it is a male, we have 27 out of 51 is the probability of that, which is the same thing as 9/17. Are being a woman and being a Democrat independent? And just from the eye test, it's probably not, but we have to justify. So the probability of being a woman was 0.49. The probability of being a woman, given that you are a Democrat, and by the way, independent here is different from the political party independent. So probability of being a woman given being a Democrat, the probability of being a Democrat in this problem was 0.4. And the probability of being a woman and a Democrat, if we look at the chart, was 0.22. So 0.22 divided by 0.4 is 55%. So 55% and 49% are not the same, so they are not independent. Can you use a table to solve this problem? Yes. Republican, Democrat, independent, total, male, and and female in total. Basically, what we have is we're taking all of the things from the edge of our chart, and then we are turning them into tabular format. So if I have all of the information that I got after I multiplied everything together, oops, this is 0.51. But what ends up happening is I end up with all this information that I got from the tree. A table or a Venn diagram is usually easier to use if you're given counts, but if you're given conditional probabilities, it's way easier to use a tree diagram, because in order to get to the table, we probably either had to do a tree diagram or we had to do all those calculations to begin with. So I can use the table, but I have to do work in order to get there. In a survey of 1,200 college students, notice that we're given counts. So since we're given counts, I can make a table. So we have all-nighters and not all-nighters. We have cheating and not cheating. So we have 380 people that, well, we have 1,200 total. We have 380 all-nighters. We have 800 cheaters. This means we had 400 non-cheaters. And we have 820 non-all-nighters. And we have 315 who have done both. So now all we have to do is do the subtractions to get everything else in order. So I have 65 all-nighter people that haven't cheated. I have 335 non-all-nighter, non-cheater people. What is the probability that a randomly chosen respondent has done neither? So that's 335 over 1,200. What's the probability that a randomly selected cheater has also pulled an all-nighter? So that's the probability of all-nighter given cheating status. So given cheating status would be 800. Pulled an all-nighter as well would be 315. So I'm just looking at that row in that case. What's the probability that a randomly chosen person who pulled an all-nighter hasn't cheated? So I'm only looking at the all-nighter row, or I'm sorry, column. So that's 380 in the denominator. And they haven't cheated, that would be 65 in the numerator. What's the probability that a randomly chosen respondent has tried at least one of them? So if I look at that, probably the best way to go about that is subtract 1,200 from 335, or I can add together all of the other categories. So 315 plus 485 plus 65 gives me 865. So I have 865 out of 1,200 have tried at least one of them. Is cheating independent of all-nighters? So let's say take the probability of cheating, and then the probability of cheating given an all-nighter, or the probability of cheating given not an all-nighter, and then see what happens. So the probability of cheating was 800 out of 1,200, which is the same thing as 2/3. The probability of cheating given an all-nighter, so if we have given an all-nighter, that's 380, and then cheating and all-nighters is 315. So 315 out of 380 looks like it's way bigger than 2/3. So that's about 0.829. So since these are not the same, that means that we are not independent. Are all-nighters and cheating disjoint events? That's clearly a no, because the probability of all-nighter and cheating is not equal to 0.